Hi everyone, welcome to the 6th video in this series on deep learning in MATLAB. In the previous couple of videos, we created our first neural network that classified digits, and then we also saw how to use DLARRAYs and auto-differentiation. In this video, what I'm going to do is I'm going to rewrite our simple neural network that classified digits using DLARRAYs. So we will write our own neural network from scratch at a low level compared to the previous video. So we won't be using the pre-made layers or the pre-calculated networks, none of that. We would be writing our own network from scratch using DLARRAYs. And since the code is going to be a bit longer, what I'm going to do is I'm going to do a code walkthrough. So I have already written the code and I have uploaded it on my GitHub page. The links for this you can find, you can find in my videos or on this video as well. And I'm just going to walk through the code that I've written, so that it's not too long. All right, so let me pull up my GitHub page. So the code is this file, number 6, which corresponds to the number of this video. And let me open it. Awesome. And I have commented the code pretty well, so that you guys can follow along, or the description also tells you what's going on. So I hope you find it helpful. And in this video, again, we will be using the MNIST dataset, which is again 0 to 9 digits, and each image, so there are the images that contain handwritten digits, and each image is 28 by 28 cross 1, which means it's a grayscale image, and the task is to predict what digit it is. So first, so I give some details on where to obtain the dataset. So if you go to this web page, you can download the dataset, and then I define certain parameters: the learning rate, the number of epochs, and the batch size. I will explain about these two later. Batch size is how many images you're taking together in your network. So I described batch size in my second video, where batch sizes are used to reduce the variance. So in one go, I will process 32 images together and then take the average of the loss to train my network. The first few bits of codes are just some pre-processing steps. I have included a pre-processing library that loads the images and loads the labels. So all it does is fills up XTrain with the loaded images and YTrain with the loaded labels. And then I need to do some pre-processing in which I do one-hot encoding of my training labels. So what one-hot encoding means is, the labels are what? The labels are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. One-hot converts them into 10 by 1 arrays, where say arrays of zeros, and there is a 1 corresponding to what the label is. So for example, if my label is 3, one-hot encoding would be 1, 2, 3, 1, and then all zeros. So let me just get this number right: 3, 4, 5, 6, 7, 8, 9. Yeah. So only at the third position there is a 1, rest all are zeros. So that resembles 3. If I wanted to say 0, so this would be the one-hot encoding for 0. So one-hot encoding is all zeros except for the index of the label, where there would be a 1. So that's all these pre-processing steps do, and they're not so important, so that's why I'm going to skip over them. So let me just run them. So it's going to take a bit of time because lots of data is being loaded in, and then I do one-hot encoding of my data. Great, so that's done. So let me just show you how the data looks like. Right, so if I open my X test, you would see that there are like 10,000. Oh, I want to show XTrain. So xtrain is my training data set and xtest is my testing data set. So the test set is what I would validate my model on. Now, just to show you, this is 784 times 60,000. So what that means is there are 60,000 samples. So the number of columns are 60,000. That means 60,000 sample, and each sample is 784 lengthwise. So why 784? It's 784 because if I do 28 times 28, so let me show that to you. 28 times 28. Sorry, I screwed that up. 28 times 28, 784. So this is the number of pixels each image has. So what I've done is, an image is like a grid. I have flattened it out. So instead of taking it as a grid, I just arranged it in one dimension. So that's why it's 784. So, and the pixel values are from 0 to 1. So 1 being black, 0 being white. So as you can see, there are some values that are between 0 and 1, and these resemble the digits that you have. Great, so that's my training data set. Remember, there are 60,000 of them. And let me show you what the one-hot encoding, so first let me show you the labels. So these are the labels, so just 5, 0, 4, 1, and so on. Now, the one-hot encoding is again 10 by 60,000. Why 60,000? Because there are 60,000 samples. And why 10? Because each sample is 10 dimension long. So, sorry, each sample has a dimension of size 10. So if you remember, the first Y train was 5. And here, corresponding to the 5th index, because the first one is 0, 1, 2, 3, 4, 5. There is a 1. And so on. So this is the one-hot encoding. So this one-hot encoding is what we will use for our network. We'll feed in the 784 dimension data, or the images that is 784 dimensions in a 1D array. And then our labels would be a 10-dimensional vector with a 1 at the corresponding location. So let me reiterate that. We will feed in an image as a 784 sized vector, because 28 times 28 is 784, and then the output should be a 10-dimensional object or a vector where 1 corresponds to the location corresponding to the digit. Okay, so I hope that's clear. And this is the basic outlook that I want my network to be. So my network would have an input of 784 neurons. Why 784? Again, 28 times 28. So each neuron takes in the value of a pixel. So since I need 784 pixels, that's why I have 784 neurons. And then I would have 2 hidden layers. So these are the hidden layers of my network. And I decide them to be of size 100 neurons and 100 neurons. And then my output neuron is, my output layer is 10 neuron wide, because my output is 10 dimensional. That's why 10 neurons. And after each layer, I would obviously have to have some non-linearity in the form of activation functions. So in my model, I will have a ReLU function or a ReLU activation after each layer. And then at the end, I would have a softmax. So remember from last video, you have softmax whenever you want to have a probability distribution. Whenever, because all the values of these neurons, I want them to lie between 0 and 1. So that's why a softmax. So this is the computation that needs to be done. So, okay, let's look at what's happening here. I get 784 inputs, and this input needs to be multiplied by a matrix over here. So I need to do A times X, if X is my input, and then add bias, and that's my input to the second layer, or the first hidden layer. So what I'm doing is multiplying my inputs by a matrix A which is called the weight matrix, and then adding my biases. The weight matrix would be 784 times 100 because the dimensions need to match. So my weight matrix that multiplies the input would be 784 times 100. The bias would just be 100, a vector of size 100, because the dimension of A times X is just 100 times 1. The same goes on, the same computation goes on for the second layer. In the second layer, the weight matrix would be 100 times 100. So it's always input dimensions times the output dimensions. And the size of bias is always the output dimensions. So just remember this as a fact, that the weight matrix dimensions are always input times the output, and the bias is always the output. Great. So when I create these weight matrices, I need to randomly initialize them. So when you create a neural network, when it's not trained, the weight values are some random numbers. And that's what I do. So for the first weight matrix, which is 784 times 100, I randomly create a value for, and I do that for all three weight matrices. Notice the first one is 784 times 100, the second one is 100 times 100, and the last one is 100 times 10, because the output dimension is 10. And the same I do for biases as well. Now a key thing, what I'm doing over here is, so this rand command, what it does, it generates value between 0 and 1. Now I want, just for numerical stability, it's good to have values between -1 and +1 in a neural network. That's a good initialization point for a neural network. So just to get that, I multiply my random numbers by 2 and subtract 1, so that the range becomes from -1 to +1. Okay, great. The next step, remember, since we are doing deep learning computations, you need DLARRAYs. So I just convert all these objects into DLARRAYs. And then I just collect them together in a cell array so that I can reference them whenever I need. So this cell array parameter contains all the parameters of my network. So let me just run this block, and good. Then with a simple function, I train my network. So what I'm doing is I'm looping a number of times, rather number of times, and then I'm applying this function every time. So, okay, let me backtrack a bit. Epoch refers to the number of times you want to loop over your training data. So if I say I want the training to loop over my data set 5 times, that means the number of epochs is 5. So here I have arbitrarily set the number of epochs to be 10. So I will loop over my data set 10 times. And then what I do is I apply this function, perform training. I pass in the training data set, the labels, what should be the right answer, the parameters of my network, learning rate, and a batch size. Okay, so the first 3 are easy because you need to pass in what my training set is, you need to pass in what my labels are, you need to pass in what are the parameters of the network. The third one is how quickly do you want the network to learn, or what should be the learning steps. This is what learning rate does. And batch size tells the network how many images should it take together. Batch sizes, it's good to have a batch size of 30, 32 or something like that, because it reduces variance. So what this function does is it trains the network, it trains on this X-train data set and returns the parameters once the training is completed. So you pass in parameters and you get some parameters in return, you get the trained parameters in return, and then you keep on doing that again and again, and specifically 10 times to train your network. This is what that does. So let's first dive deep into what this perform training does. So let me scroll below and I reach perform training. So again, it takes in input, output, which input is the training set, output is the labels, parameters, learning rate, and batch size. First, it does some computations to perform how many batches there are. So I'm performing a computation to figure out how many batches are there, and then just get the size of batches and size of images. And then I loop over the mini batches. So say I have 100 samples and my batch size is 10. That means I have 10 mini batches. Each mini batch has 10 images. So that's what a mini batch is. So this is pretty straightforward stuff. I'm looping over the mini batches, and in each loop I am getting I'm slicing the test set to only contain the mini batches. So here you can see I take the whole size in the X dimension just to get the whole image, and then I only count the number that correspond to a particular batch. So this fancy stuff is just basically take here in the first iteration I would take the first 32 samples. In the next iteration I'll take sample number 33 to sample number 64, and then 65 to plus 32, whatever that is, and so on. So here I'm sequentially taking images and the labels. Good. Once I have them, I pass them into another function called train, where I pass in this mini batch with my parameters. So this train function, it has been wrapped by this DLFEval. So if you remember from our previous video, you use DLFEval whenever you want to keep a track of derivatives. So here we will keep a track of derivatives, and what is this function returning? This function is returning two parameters or two quantities, the gradients and the loss. So I will go into the details of this function in a bit, but for the purpose right now, just know the fact that this function returns the gradient and the loss. So good, we get our gradients and we get our losses. Awesome. Now all we do is we loop over 6 times. So basically we loop over the elements of my parameter cell array and then move them in the direction of the gradient. So let me unwrap this. Why loop over 6 times? Because if I go above, my parameter contains 6 quantities, the weights and the biases. That's why there are 6 of them. Okay, good. So I'm looping 6 times, and each time what I'm doing is, so the gradient is also a cell array which corresponds to the parameters. So I take the specific parameter, I take its specific gradient, and then I subtract it from its original value times the learning rate. So this is standard gradient descent. So my parameters are moving a tiny bit in the direction where the loss reduces. This is an important step. This is the crux of gradient descent algorithm. And then just in a temporary variable, I'm storing the total loss. And then suppose, so this last bit of code is a simple code that takes care of images that are not in any batch. So suppose I had, let's take the example of when I have 101 images and my batch size is 10. So that means I have 10 mini batches and then I have 1 remaining image, because that I can't divide 101 by 10. So this remaining bit of code takes care of those remaining images. And then I display per epoch loss. Great. So now let's go further into this train function, which is supposed to return the gradients. Now, okay, so this is an important function as well. From the declaration, you can see that it gives you the gradients and it gives you the loss. What it takes in the input of the mini batch, the output, and the parameters. There are 6 parameters, so I again unwrap, I open it up and store them in these variables. And then here is where I perform the main computation of our neural network. So if I go back again, the computation that needs to be performed is AX plus B. That is what a linear layer does. So here, my input is multiplied by a weight, and then the first bias is added. That's my first hidden layer computation. And then I apply a ReLU nonlinearity to it, store it in A1, and then I do the computations for the next layer. For the next layer, I take the input of the previous layer, multiply by its weights, add a bias, and then apply ReLU again. So these two computations are the same. So this is what a fully connected layer does, and we have two of them. And finally, I get the computations of my final layer, and then I apply a softmax. I apply a softmax because softmax gives you probabilities, and this is what we need. Right, so here there is an additional parameter called data format, and it tells you, this just tells MATLAB rather, what the dimensions of my DLARRAY are. So BC means the first dimension is batch, and C means the second dimension rather is channel, or it's what contains data for each element in the batch. Great. And finally, I do a cross entropy loss. You can read more about it. Let me see if I can open the help on this. So cross entropy loss is something that is used whenever you have data categories and you want to perform loss on categorical data. So since there are like 10 kinds of categories, 0 to 9 digits, so that's why cross entropy is the loss most useful in this situation. I pass in my output, and then what should be the real result. So cross entropy requires the output and what should be the target. And again, I pass in my data format here. Actually, I can show you what cross entropy loss looks like. Let's see. Right, so this is the basic. Let me try to find a simple example. Okay, so I can explain from here. So this is how cross entropy loss looks like, where Px is the predicted, and this log Q. So Px is the target, and log Q is what's predicted. So whenever the targets are 1, if the target is 0, this term does not exist. So the sum is over all the digits from 0 to 9. So for each digit, what is the target? Because remember, we are doing one-hot encoded. So for each, the outputs are 10-dimensional vector. So for each element in this 10-dimensional vector, you take the digit of each element and you apply this, where Px is the target and log Qx is where Qx is what's predicted. I'm sure there are better versions of this equation all over the internet, but I'm not gonna spend time on that. Great. Finally, you can just sum up the losses by using a simple sum, and then this is where we calculate the gradients. DL gradient calculates the gradient of the total loss with respect to the parameters. So pretty simple. All we needed to do was forward propagation. All we needed to compute was how our network computes the output given the inputs, and DL gradient takes care of computation of the gradient. Great, so these two functions are the crux of our training loop. Now let me go back and run our training. So, okay, this is going to take a while, so I will pause the video and resume once the training is done. Okay, so it took about a couple of minutes, but the training is done. Now here you can see I was printing out loss every epoch, so this is the averaged out loss. And as you can see, it's decreasing. In the first epoch it was 2.7, and then it became 0.7, 0.5, 0.4, 0.3, and so on. So in the first few epochs, the loss reduced drastically, and then it slowed down. The reduction in loss was less and less and less. So here's a trade-off between the time you want to spend training compared to the accuracy. that you might want to think about. Great, so we have trained our network. So what does it mean to have a trained network? It means that you have some parameters for your network that fit very well to the training data. So these parameters are the important thing. So you have your network which has thousands and millions of parameters, and you want them to be trained, and that's what we have done. So these parameters are such that they can figure out what digit it is. So now that we have trained our parameters on the training set, let's see how good or how well they perform on the test set. So if you remember, well, I probably never covered it, but what I had done is I had also created a test set as well with test labels as well. So, and this test set contains about 10,000 images. So we will basically perform test, apply this function perform test that takes in this test data set and the parameters, and again the batch size and what should be the labels be. And then I find out how many are correct, how many labels match, where the true label matches the predicted label, and that gives me the accuracy. So let's run this. And as you can see, the accuracy is 90%. Not bad for a simple network. So that's pretty good, I would say, for now. Then just to see things and things working in real life, let me just pick a random image and I display the image over here. So this is a 4, and then what I do is I run this image through my network using this predict function, and I see what the prediction is, and it's a 4. The label is a 4 and my prediction is a 4. So my network works pretty well. Let me try some other digit. So let's see. This is a 1 and the label is a 1 and the prediction is a 1. Awesome. So it worked pretty well. Let me just quickly go over what the prediction function does. So this prediction function basically runs an image or an input through my network using the same computations and the same softmax, but it does not calculate the loss because we just want to get the output. And finally what it does is it takes the maximum value. So what this line is doing is it's computing the argmax. So when you use max function, it returns two things. First, the maximum value and the index of the maximum value. We don't care about the maximum value, but we care about its index because that's what the label is. And since MATLAB is 1 index, that's why I'm doing an offset of -1. But this function takes an image and outputs the label, the true label, not one hot encoded, just the true label, what it should be. Or rather, I should say, the predicted label from the network. The perform test function basically it takes in images as a mini batch. So here I'm doing computations of mini batches, and then again runs it through the predict function and then computes how many predicted labels matched with the true labels, and then there is a running sum. So this is a helper function that is useful in calculating the accuracy of my network on the test data set. But the main function is predict, which is doing all the work. So in training, the main function was train because that was doing the computation and the gradients. In perform training, what we were performing was backpropagation. We take the gradients and move my parameters in the direction of the gradient. So this is how a custom network looks like in MATLAB. So all you have to do is figure out what computations you need to perform, and then just perform those computations sequentially, and MATLAB will take care of the gradients by DL gradient and DL feval, and then all you need to do is move your parameters in that direction. So this simple network was pretty simple because it only had fully connected layers and the output. But this method works for any sophisticated kind of network. You can do you can write whatever network that you want from scratch. But in ideal situation, you will just use layers. As I talked about in my fourth video, you will use fully connected layer or convolution layer and build your network out of those. But if you wanted to see what goes under the hood, or if you wanted to write your own architecture, is when you will start using DLARRAYs. And I hope this simple network showed you the power of DLARRAYs and auto differentiation and how to go about writing your own network from scratch. Just as a final word, you can find my code on my GitHub repo, and the link for this repo is in the description for this video. And thanks for watching. I'm thinking, what should I make for the next time? Let's see. I'll probably talk about data stores, but let's see. Thanks for watching.